take part 1 of the real new topic of today. You could call it the new operational topic, a new tool that we're going to learn. We start with an example, as we often do, where we're going to use the new tools that I will teach you now. Let's have a look at the example here. Small example for us to be able to play around with it. It's a study desired to investigate if there is a difference in energy usage for different types of work. In this case, we are looking at 9 secretaries and 9 nurses that have been measured, their energy expenditure. The measurements are given in the following table. We have, was that 9 secretaries here and 9 nurses. Now there's the same in numbers. There could have been 8 in one group and 10 in another group. That will not ruin what we're going to do now. So we have 2 samples. Now compared to earlier, it's not only a single column of data, it's 2 columns of data, right? Given by 9 secretaries in one group and 9 nurses in another group. Some measure of how much energy they have spent during a given time. Now, computationally, it's still simple. Sorry to claim, but I believe we are not doing computationally wise much more than we were taught in high school, at least not much more than I taught you on day 1 in this course. Basically, what we need to do is, and then if I should be, I realize I'm a bit sloppy or have been, I should maybe use a small x1, x2 when I use small s1, s2 here. Just basically, we have just the mean and the variance in each group. That's the computationally wise, what we're going to have a look at. What we are going to do now is to put in the comparison of those 2 groups. Of course, we want to compare the mean energy use for the secretaries with the mean energy use for the nurses. That's what we're going to do, of course, I think, given the setting. We're going to put this into hypothesis testing framework, and here it comes. The null hypothesis, we're going to test when we have 2 means in play, mu1 and mu2, is in general terms testing that the difference between the means are a fixed value. I use the notation delta here just to speculate that we could test that the difference would be 1, or the difference is 2, or the difference is 3. The test that we very often will use, at least in the first place, is testing that the difference is 0. That is a relevant test because that is the test that is equivalent to testing whether the 2 means are the same, right? Then, here I have shown you a 2-sided alternative. Just as a single sample case, we can have the 1-sided also in play. Here's the test statistic, a new tool for you. At least level 1, we're going to have 3 steps. As you may remember, a couple of weeks ago, we had this first version coming here, and then there is 1 or 2 more versions of more or less the same test statistic, but in slightly different versions. I think the test statistic makes sense. Let's have a look. What does it do? It takes the difference between the 2 means. So it takes the data, x1 minus x2 bars, and compare with the hypothesis, just like we did a couple of weeks ago, right? That makes sense. Then it divides by something. What does it divide by? Well, I would say that it divides by the standard deviation of the sampling distribution of the relevant test statistic. What if I next time, if I do a new double experiment or a new 2-column experiment, and once again compute x1 bar and x2 bar, compare those 2, then the difference would come out differently, right? The next time I take 9 nurses and 9 secretaries, there would be a new difference coming out between the two set of averages, right? Average 1 minus average 2. So there is a sampling noise, sampling uncertainty in the whole setting. So we sort of, the sampling thinking, the sampling uncertainty, which is the core of being intelligent about looking at numbers, we apply sort of to the whole situation, saying that the next time I have 2 averages, they come out differently. The next time I have 2 averages, they come out differently. The next time I have 2 averages, they come out differently, right? So I have to think about what is the variability in such a difference between 2 averages, right? But that is, again, I hope you can realize that such a thing actually is something that I should emphasize here. I forgot to put the bars. It's the capital X1 and 2 bars. The averages considered as random variables themselves because they change from sample to sample. We can use, I'm not going to go through all of this, but just indicate we can use the variance rules like this. And then we have already seen from single sample. So this is just using what I would say variance calculation rules that you have already at least had the opportunity to practice if you followed the exercises. So I just again have something, a standardized difference between data and hypothesis, right? I see the difference between data and hypothesis. I standardized by the noise of such a thing, like I did 2 weeks ago for a single sample. Then the theory tells me, now, this is where the theory is nice. The theory tells me that if the hypothesis is true, meaning that the average of these 2 really is the same as delta, that means that on average it's 0 on the top, then the test statistic follows a standard normal distribution. And this is where the theory comes in and tells me what is to be expected of this test statistic alone due to random variability in the system. That's the standard normal that tells me. That's what I should use as a kind of measurement stick for telling whether I'm far away or close to, whether the data is far away from the hypothesis or close to the hypothesis. And then we are back in business. Having computed this set statistic, we just do the hypothesis test exercise, you could say, exactly as you were taught 2 weeks ago, which I repeated, at least in general terms, a few minutes ago. You just do the same thing again. And the same thing comes here. You may have realized you've seen such a table before. This is a critical value way of finishing off a hypothesis test story, saying that if I do a 2-sided test, I should reject if my computed test statistics is either too small or too large. So if I'm too much to the right or too far out to the left, I will reject the hypothesis. If I would be in a sort of right-hand side, one-sided situation, then I will reject if I'm too large to the right. There is a difference here when it's a 2-sided. We spread the probability with alpha half on each side. When it's a 1-sided case, like this, we have all the alpha probability in the right tail. So that's the difference, the technical difference when we look at these. And then the final one, and this one would be to reject if I'm out here with alpha to the left. Here is version 2 of the same thing. Here is version 2 of the same thing. Not assuming, maybe I was a bit fast there, I forgot to emphasize that I was in the first, I'm back to the first version, sorry for jumping, I'm back to the first version. I was assuming that I could just plug in some known values for the sigmas, right? The sigmas enter the formula, so I would have to know the sigmas to be able to use this formula. So that's where the theory is nice. Then the standard normal comes out as the theoretical sampling distribution. If I do not know these in advance, and that is what we call unknown. Unknown does not mean that I have no information. It just means it's a bit unclear wording. I remember I was confused about this wording myself. How many years ago? 84. What is now? Now we have 12. That is 28 years ago when I learned this for the first time. And 27.5 years ago, when I was at my first statistics exam, I was still confused about this wording and make some major stupid mistakes that I'm sure my teachers thought, this guy, I hope he'll never come out and work as a statistician out there looking at those stupid mistakes he was doing in that exam. And then here I am. I thought, hey, I'm going to do this anyhow. So, yeah. Probably I still do stupid mistakes, that's part of life, but hopefully I increase the bar a little bit on where the mistakes are being done. Just to say, I realize that this can be challenging wording. What I mean by unknown is that we have to compute them from the data, not assume them given as truths, as some numbers we can plug in. So we compute the variances given the data we have and we plug them in. And that gives us something additional to think about when we are going to consider the probabilities. However, if, where does it say, blah, 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 blah. Here it is. If the samples are large, I don't say exactly how large they should be, but at least this one would be a pretty safe thing. If we are above 30 on each of them, usually that's what we call large in this course. It's not a sort of black and white thing, but that's our rule of thumb here. Then we can just still use the standard normal, just do as before. That's the second version. And here's the same table as before, so it's a complete copy. So I'll not say any words. I could repeat the same words from before, but I won't do it. Since I believe now it's time to take a well-deserved 15 minutes break. So let's do that.